Thank you very much for inviting me. It's always a pleasure to be in University of Washington, even in virtual format. So I will talk about water waves today, and I will mostly focus on the numerical methods. And my collaborators on this work are some of the people who are currently sitting in the audience: Anastasia, Bernard, Pavel. This work is based on what we did together with Professor Alexander Karatkevich and Professor Alan Newell, especially related to the white capping phenomena. And I will try to give kind of an introductory talk of what we're doing. So first I will start with the formulation of the problem that we're interested in. So here you see a photograph of the wake of a boat in a canal in Netherlands. And here you see that the shape of the waves in the wake of a boat looks like it's almost parallel waves. Can you guys see my mouse too, or not? Oh, cool. So you can see that the wake of the boat consists of roughly parallel waves, and there's very little that's going on in the transverse direction to the propagation of these waves. Most of the surface changes in the direction along the wavefronts, perpendicular to wavefronts. So we can think of the shape of the surface as being just a function of one-dimensional variable that's perpendicular to wavefronts, and also another direction that would be important is the direction towards the depth of the fluid, or from the depth of the fluid upwards. So here's a kind of a geometry that we're mostly working with. So on the left, you see a three-dimensional fluid with a 2D surface, but you see that when there is little going on in the transverse direction, you can kind of throw away the transverse direction and just think of variables x, the horizontal variable, and the vertical variable y. So in such a case, it's nice to think about a function y equals eta of x and t that represents the free surface. It's a function of x, but also a function of time, because the surface shape is moving and it has different positions at different times. About the fluid that's below this free surface, we will say that it's going to be ideal, meaning that it's incompressible and inviscid. So incompressible means that density is constant, or speed of sound is infinite in the fluid domain. And this will also imply that the incompressibility condition, divergence of velocity, will result in the Laplace equation once we make the assumption of potential flow. The velocity being the gradient of potential, we have divergence of velocity, that's divergence of the gradient of phi. Phi is the velocity potential, so divergence of the gradient, that's exactly the Laplace equation for the velocity potential phi inside the fluid. On the free surface, we will assume that we will have forces of gravity always, almost always, and sometimes if we get to the white capping thing, surface tension effects will also be considered, but most of the time we'll be just focused on the forces of gravity. Also, atmospheric pressure is kind of way too complicated, so we will ignore it. Now, from a mathematical standpoint, we are working with a fluid which occupies the domain. In the horizontal variable, it goes from minus infinity to plus infinity. In the vertical direction, it goes from minus infinity, unless we're interested in the finite depth fluids. So in that case, we don't have minus infinity, but rather we have minus h to eta for the vertical extent. But finite depth is also a much more complicated problem than infinite depth. So for now, we will just settle with the infinite depth problem. So in vertical extent, infinite line from minus eta to, infinite, semi-infinite line from minus eta to, from minus infinity to eta. And here really the shape of the domain, this eta of x and t, is a part of the unknowns of the problem. So we really have the shape of the domain coupled together with the Laplace equation, which we solve inside the domain, which is kind of specified as a part of the solution. So this kind of makes things more complicated than just solving Laplace equation in a fixed domain. And together, to this Laplace equation, we also need to specify some boundary conditions. So one of the boundary conditions involves eta, that's the shape of the domain. And the second boundary condition, this one is also sometimes called the Bernoulli equation. Essentially, it's integrated Euler equation. And this tells us about how the potential at the free surface depends on time. This dphi by dt is a time evolution equation for the velocity potential at the surface. Well, unfortunately, this equation also involves a gradient of phi, and a gradient of phi, you have to know it throughout the domain in order to be able to evaluate the full gradient, right? Because if you only know phi at the free surface, you can only differentiate in the direction tangential to the surface, but not in the normal direction. So that's why Laplace equation will not completely disappear from this problem, as would be really nice. And the third boundary condition that we have here, so the first two, see, they are posed at the free surface at y equals eta of x and t. And the third one is posed at the infinite bottom. That just tells us that the normal velocity at infinite bottom is equal to 0. So just saying there's no fluid flow through the bottom at infinity. And at this point, it's nice to introduce a conformal mapping approach. So this was originally done by Stokes himself for the traveling waves. But for a fully time-dependent problem, this was first introduced in the work of Ovsyannikov in 1973, and then was very hugely successful in the works of Tanvir in 1991. The idea is that you take a auxiliary plane, the conformal domain, which you parameterize by the variable w, u plus iv, and you make a conformal mapping from the lower complex plane on the right to the domain of the fluid on the left. So here, fluid is below this blue line and air is above, or vacuum is above. So a conformal mapping will do a mapping from a lower complex plane on the right to the fluid domain on the left, below this blue line. And the conformal mapping, Z, we call it Z. If you evaluate it for the boundary of the conformal domain, namely at the real line, you will simultaneously, this line is mapped into the blue line on the left. So if you evaluate your conformal map for real values of argument, setting v equals to 0 here, you get points from the free surface on the left. Right, so you consider some points, say u equals 1. This would correspond to some point at the free surface on the left. It would be x of u, comma t plus I y of u, comma t, right? If you choose a point with coordinate u. And the conformal map, it's has both real and imaginary parts. And since conformal map has to be an analytic function in the conformal domain, it has to satisfy certain relations between its real and imaginary parts when evaluated at the free surface. So namely, the imaginary part y is connected to the real part x by Hilbert transform. So the nice thing about having a conformal map is that if we have an analytic function in the lower complex plane on the right, this will automatically also be a analytic function inside the fluid domain in the variables x and y. So harmonic functions under this transformation remain harmonic functions. And so the thing now, however, that we get that might not be as convenient as before. So now instead of finding just one function eta of x and t, now we have to determine this complete complex analytic function z that makes a mapping from lower complex plane to the fluid domain at every single instance of time. So in fact, we are going to get some evolutionary equation for the conformal map. So that's this equation dz by dt. And in addition to that equation, we will also have some equation on how the value of the complex potential, which we defined as velocity potential plus I times the stream function, how this complex potential also depends on time as time evolves. So that's the second equation. Those two equations are completely equivalent to the original system that's written down here. And so what you also can see in this system is that you get these functions capital U and capital B involved. So those functions are defined in terms of so-called projection operator, P hat. This projection operator is essentially is related to the Hilbert transform. This P hat is just 1/2 plus I over 2 times the Hilbert transform. This makes this set of two equations not just a set of two PDEs, but rather two integral differential equations, because not only we have derivatives with respect to U, we also have integral transforms in these functions U and in the function B as well. Okay, so I will show, if there's time, I will also show some simulations of these equations, but let me first mention that the system that we are talking about here is Hamiltonian. And it turns out that the variables eta and psi is the value of the velocity potential at the free surface, are the two canonical Hamiltonian variables, as was originally discovered by Vladimir Zakharov in 1968. And the significance of that is that you can write down the Hamiltonian only using surface variables eta and psi, and you can write down the equations of motion just by standard classical mechanical means. You can write down the equation for d eta by dt, and this would be equal to just variation of the Hamiltonian with respect to psi, and d psi by dt would be dh by dh by d eta. And moreover, if you consider, so let me also step back a bit here. So the Hamiltonian that you see here is not written just in terms of surface variables. So the second integral and the third integral are in terms of the surface variables. But the first integral that you see here is an integral over the entire fluid domain. So see, you have to integrate with respect to dx, but you also have to integrate from -infinity to eta, so throughout the entire fluid domain. But this turns out that can be easily fixed if you use the integration by parts on this integral. You throw one of the nabla operators from nabla phi onto the other nabla phi. See this nabla phi squared. So you get phi times Laplacian of phi. Laplacian of phi is 0 by incompressibility condition. But you also get the terms from the boundary. Contribution from the boundary would be phi times the Dirichlet-Neumann operator applied to phi. And this Dirichlet-Neumann operator is a rather complicated beast. You can either work with it in physical variables, and then you would write an expansion of this Dirichlet-Neumann operator around the flat surface, and you will get the so-called Craig-Sulem expansion, which is infinite series and not always easy to work with, especially if you're considering high amplitude waves. Or since we did the conformal mapping approach, we can explicitly write these integrals in terms of the conformal domain. And in conformal domain, remember the surface shape is always flat. right? Because here we always, by definition, seek conformal map that maps lower complex plane into the fluid domain. So the shape of the surface in conformal domain is guaranteed to be just real line. And this really simplifies stuff in terms of Dirichlet-Neumann operator. So this dphi by dv is essentially what is left out of the Dirichlet-Neumann operator. This dphi by dv is the differentiation with respect to v variable. So remember this q plus iv. V is the vertical direction. So dphi by dv is the derivative of phi with respect to variable v and with respect to vertical direction. So it's essentially if you have phi, the velocity potential, you take the derivative with respect to v, that's the normal derivative at the free surface. And then you can also write down a bunch of relations like stream for the stream function and use the Cauchy-Riemann relations. You can write that stream function is Hilbert transform of psi. This is just a property of analytic function evaluated at the real line. And then dphi by dv, you can rewrite it as minus d theta by du using Cauchy-Riemann. Theta is minus Hilbert transform of psi. So you essentially write dphi by dv just in terms of the value of the potential at the surface in terms of psi at the surface. Of course, you get this Hilbert transform, but that's kind of much easier than if you had to solve Laplace equation in the original fluid domain to determine what's the Neumann condition corresponding to a given Dirichlet condition. Okay, so now let me go to the Stokes waves. So Stokes waves, they are fully nonlinear waves that propagate over one-dimensional fluid. There's a family of these Stokes waves going from waves of small amplitude all the way to the so-called limiting Stokes wave, which is represented here on the figure. So the limiting Stokes wave has a 120-degree angle at the crest, and it's a rather peculiar object. Usually we will not be able to make any numerical simulations of exactly the limiting wave, but it would be always interesting to kind of approach the limiting Stokes wave as much as we can, at least when we're talking about high amplitude waves. So what's known about Stokes waves? Well, periodic trains of Stokes waves were first determined to be unstable by Benjamin and Fair. So it's called now Benjamin and Fair instability. I think it's a result from 1967 experimentally it was found that Stokes waves are unstable. And then in the work of 1968, Zakharov showed that mechanism of the instability of trains of Stokes waves essentially can be understood as the modulational instability that occurs also in the nonlinear Schrödinger equation, where constant envelope has a modulational instability, and essentially you can think of this constant envelope as being the envelope of train of many Stokes waves, and since there is a modulation and stability in focusing nonlinear Schrödinger equation, it also carries over to the water waves problem as well. But it turns out that large amplitude Stokes waves are also unstable to superharmonic instabilities that are strongly localized near the crest of the wave, and presumably they lead to overturning of steep ocean waves. So how to find those Stokes waves? It's you cannot write down, well, at least, I mean, I don't know if it's possible. Well, yeah, okay. So it's not possible to find Stokes waves explicitly to write a formula for them, but you can find them numerically. Or you can write, in fact, asymptotic formulas for Stokes waves, the so-called Stokes wave expansions. But if you want to explicitly write down, if you want to find explicitly a solution to the a traveling wave solution to the Euler equations, then you typically have to do this in using some kind of numerics. The numerics is done as follows. You take the Bernoulli equation and kinematic condition, you plug in the ansatz of a traveling wave for the velocity potential, identity transformation plus a traveling wave into the conformal map, you enforce periodic boundary conditions, and you get the so-called Babenko equation, which was first derived by Babenko in 1987. And then you can solve this Babenko equation numerically. It's actually a very nice equation to solve numerically because it has some really nice adjointness properties for its linearization operator, which I will show later would be important. So here are a few solutions of the Babenko equation, few Stokes waves. You can see that if you consider small value of speed, so here speed is measured in units of linear gravity waves. So in other words, in units of square root of g over k. So if c equals 1, this is in dimensional units correspond to square root of g over k. If this is more than 1, this is more than the speed of a linear gravity wave. And you can see that if the speed is very slightly different from the speed of gravity, linear gravity waves, you get fairly mild, almost monochromatic wave as in the yellow curve here. But if you try to push and increase your speed of the wave to be larger and larger, as for the red and the green curve, then you see the wave becomes more and more nonlinear. In fact, if you push higher and higher, you will see you will get to this blue line, which has almost a crest-shaped, almost an angle-shaped crest, almost 120 degrees here. This wave is still regular. It's just when you look at it from afar, it looks like it's almost an angle here. But if you zoom in close enough, you will see it's still a regular wave. It just has a very small curvature radius near the crest. Okay, and it turns out that if you continue towards the limiting Stokes wave, then this parameter c, the speed of the wave, starts to oscillate. And so you can get waves that are steeper than the blue one with the speed both larger and smaller than the value presented here. So you have infinitely many, in fact, oscillations as you approach towards the limiting wave. And not only c, not only the speed of the wave goes through these oscillations, but also other integral parameters of the wave, like the Hamiltonian and momentum. All right, so now let me also say a few words about how to solve numerically Babenko equation. This is the Babenko equation, by the way. You can ignore this c squared over c naught squared. I usually replace it with just one letter c squared, but here it's, yeah, forget about this c naught. You can think about this as just the speed of linear gravity waves. And the nice thing about the Babenko equation, it has explicitly this linear part and a quadratic part. Also, it involves this operator k hat, which is precisely our Dirichlet-Neumann operator that you have seen already in the slide with the Hamiltonian. It's basically a combination of derivative and a Hilbert transform. And this equation can be solved quite efficiently by Newton conjugate gradient method. So the idea is that suppose that somebody provides you initial guess, y superscript n, or you find it from some asymptotic expansion or by other means, maybe you get some result from the previous iteration. This is some approximation of a imaginary part of the conformal map. Then you can think of the true solution of the Babenko equation as this solution at the current iterate plus some delta y. And you know that on a true solution, if you apply Babenko operator to the true solution, you're supposed to get a 0. So that's what you write on the left-hand side here. But then you can linearize around your current iterate. So here, by the way, the subscript k just denotes that it's more convenient to do this procedure on the Fourier side rather than in the U space. So you can write this equation either in Fourier space, or you can by just taking Fourier transform of this entire equation, or you can look at this equation as is. Turns out that on the Fourier side, things converge a little bit nicer than in U space. Anyway, so when you apply this operator of the Babenko equation to the current iterate plus correction, you can linearize at top of the current iterate, writing down L naught applied to the current iterate plus some operator L1, which is the linearization of Babenko equation, applied to delta y. And y superscript n you already know from the previous stage, so you can apply this operator L naught easily to something that you already know. You can think of this as being your right-hand side. And delta y is something that you need to solve for. The operator L1 is also can be explicitly found from the Babenko equation as well. So you end up having to solve a system of the form L1 times delta y equals to minus L naught times yn. So this system right here. And now it's important to know the adjointness properties of L1. If L1 is a self-adjoint operator, then you can write down this system and solve it with a conjugate gradient method or minimum residual method or any other method that is well suited for self-adjoint operators. Typically, those methods are more efficient than the ones when L1 has no self-adjointness properties, like the GM-Press, for example. So once you solve the system, you can update your current iterate with the solution that you found, and you're back to step one. If you already have sufficiently good approximation of the solution, you can stop here. If not, you can continue this sequence of steps indefinitely until you reach a required tolerance. Okay, so let me then skip some of the things about the singularities properties of the Stokes wave, and now let me mention some new results about the stability of Stokes waves. So first of all, how do we determine the stability of a solution to an ODE or a system of ODEs? Well, we can think of the equation y prime equals to f of y. And suppose that we already found some exact, say, stationary solution of this system. So if it's an ODE, then stationary solution would be just a constant vector y naught. So what you would need to do is you would need to linearize on top of this stationary solution, and then study the eigenvalue problem associated with the linearization. So basically, we consider y in the form of y naught plus delta y, plug it into the ODE, linearize this function f of y on top of y naught. We get this Jacobian df evaluated at the exact solution y naught. And this is now just a first order nice linear equation in time. The solution of a first order linear equations is just given by exponential. So we look for a solution in the form of delta y equals to some e to the power lambda t times vector u. And once we plug in this ansatz into the system, we get a really nice eigenvalue problem with a matrix Jacobian of f evaluated at y naught applied to vector u equals lambda times u. So now, if we're interested in the stability of the solution, then we need to look at what values of lambda we get. If we get any values of lambda that have positive real part, this implies that our ansatz delta y equals e to the power lambda t. We'll have some positive real part multiplied by t. So as t goes forward, as t increases, you get u being multiplied by larger and larger values, right? If you have e to the power, say, 5t, then as t grows, this exponential would be growing also. So you'll be seeing some sort of linear growth of instability. On the other hand, if, for example, your eigenvalues all have negative real parts, this would mean that this exponential will be just decreasing forward in time, and your perturbations will not be growing, but rather will be decreasing. Well, since in our water wave problem, it's a Hamiltonian system, there is certain symmetries that are involved, and the eigenvalues lambda, they have to appear in the so-called quadfold symmetry. So if you have an eigenvalue in the complex plane at lambda, you also will have an eigenvalue lambda bar, minus lambda bar, and minus lambda. So eigenvalues can always appear in sets of 4 if they're in the complex plane. If they're on the xi, like on the imaginary axis or on the real axis, then you can get away with just 2, because I mean either lambda and lambda bar will coincide on the real axis, and on the imaginary axis you would have lambda bar coincide with minus lambda, right? So essentially, we're going to figure out how to solve this eigenvalue problem in the most efficient way as possible. So the analogy with the ODEs is, of course, simplification of the process that we're going to do with the Stokes wave that we have found in the previous step. So we know that a Stokes wave, when viewed in a reference frame traveling together with its speed, is not going to. I mean, if we go to a reference frame that is traveling together with the speed of the Stokes wave, then the shape of the surface doesn't vary in time, right? So we get exactly a stationary solution of a system, which is exactly what we need for part 1. So the next step would be to so the different thing between the ODE and the PDE case is that in the ODE case, this vector u was just a vector in Rn. But in the PDE case, we have some options what our disturbances can be. They can be either co-periodic with the Stokes wave, in such a way we'll call them superharmonic, or they can be not related to the period of the Stokes wave whatsoever. So, for example, think of your background solution being 2π periodic, the Stokes wave being 2π periodic, and the perturbation has some arbitrary different period or has no period whatsoever. That's also possible to consider. It's a little bit more complicated than perturbations that are co-periodic with the Stokes wave. So in the first case here, when we study co-periodic case, it's kind of a more or less toy model. But when we consider quasi-periodic perturbations, we need to use the Bloch or Floquet theory, and this will imply that we will need to change our original eigenvalue problem to something different, some modified eigenvalue problem but essentially this modified eigenvalue problem would be written down for another co-periodic eigenfunction. So this modified eigenvalue problem for a co-periodic eigenfunction will translate to a quasi-periodic eigenfunction of the original problem. So essentially we can always reduce to considering eigenvalue problem for some co-periodic function. Okay, so how do we do the second step of our solution? So first we need to write down the linearization of equations of motion. We need to write the linearization of this function f. And remember, we need to do this in the traveling reference frame where the Stokes wave is a solution that doesn't depend on time. So we take the equations of motion that we get from variation of action through the least action principle. We make an ansatz for psi for capital Y and for capital X to be a traveling wave plus a correction. And this results in the following system of two equations for delta phi and delta Y. So it's now a system of two integral differential equations, but the important thing is that it's a linear system in deltas, in delta phi and in delta y. So it's exactly first order linear ODE, PDE, for the functions delta y and delta phi. So we can seek its solution again in terms of combination of exponentials. So some eigenfunction v times e to the power lambda t. And also to respect this quadfold symmetry, we can also add the second term w e to the power lambda bar t. So what's different compared to the problem that we considered in ODE is that this equation is resolved for the time derivative. We have y prime equals to f of y. The equation that we have here are not resolved for time derivative. So when we plug in this ansatz, we will also get not only just delta phi t and delta yt equal to some right-hand side. Instead, we would have some operator L hat involved. And this operator L hat is in fact related to the fact that delta phi and delta y are not the canonical Hamiltonian variables. And this operator L hat is related to the symplectic operator of the non-canonical structure of the equations of motion. But other than that, it's pretty much analogous to the ODE problem, except that now we have two matrices, M and L, and rather than having matrices of coefficients, we're going to have matrices with operators in them. So the operators would be somehow related to the k hat. For example, this operator M that you get on the left-hand side, it's a diagonal operator, Bloch diagonal operator. So here you have k hat in the first diagonal entry. K hat is a self-adjoint operator. S1 hat also self-adjoint operator. It's the linearization of the Babenko equation, which I previously called L1, but here I decided to switch to S1 to kind of really underline and underscore the fact that it's self-adjoint. And the operator L hat is just some operator that's not particularly nice at first glance, but the nice thing is that it can be inverted explicitly. It can be inverted by hand. Okay, so we're going to work with this system MV equals lambda LV, but before we work with it, we will also modify it a little bit to make things a little bit nicer. Turns out that we can introduce the canonical Hamiltonian conformal variables by applying the operator omega 1, 2 to the psi, the function psi. And then the variables p and y would be the canonical Hamiltonian conformal variables. And this was found in the work Dyachenko, Lvov, Zakharov in 1995. The Hamiltonian can be written down in the variables p and y, but it's not pretty. You see, you have this omega 1, 2 dagger. Dagger means adjoint operator to omega 1, 2. So it's not particularly nice, but it's a doable exercise. In these variables p and y, you can rewrite the eigenvalue problem as follows. All of these operators are operator R is related to the inverse of the operator omega 2, 1 and omega 1, 2. I will kind of skip the details. I think they're a little bit too tedious to kind of write down. These operators R, M, and R dagger. Look at the structure of what you have on the left-hand side. It's by construction a self-adjoint operator. Because M was self-adjoint, and such a combination, when you have R on the left and R dagger, the adjoint operator on the right, automatically makes this a self-adjoint thing. And again, the operator J is also can be written down explicitly. It becomes much nicer than the original operator L that appeared in this eigenvalue problem. Okay, and it turns out that you can also explicitly write down the so-called shift-invert operator associated with this eigenvalue problem. And this would be important when we start looking for eigenvalues, in particular when we'll be interested in finding eigenvalues located closest to a certain point in the complex plane. So let me kind of now describe how the numerics of finding an eigenvalue of this operator look like. So instead, there's several ways how you could do this. In principle, you could take the operators that you have in the system, and you can form a matrix of coefficients for them. So for that, you just take this operator, apply to each and every Fourier harmonic, and record the result. You would get certain coefficient. If you have, for example, n Fourier harmonics, you would need to apply this operator to each of those n harmonics. That's n squared operations and n squared log n operations, and you would get matrix of coefficients as a result, matrix of n squared coefficients as a result. And if your n is sufficiently large, then the requirements for the size of this matrix might be just too large. For example, if you have 1 million Fourier modes, then n squared is already 10 to the 12, and that's already beyond capabilities of computer. So instead of that, we would want to consider some numerical method that does not rely on forming the matrix and does not rely on storing the matrix of the coefficients. And such methods exist. Such matrices are one of the examples of such method is, for example, the power iterations. So power iterations, the idea behind that method is that you build iteratively a sequence of functions that converges to the eigenfunction that you're seeking. So, for example, if we consider some initial function f naught of x, we can expand it in a series of eigenfunctions of some operator A as follows. And these Vn's, they are the eigenfunctions associated with eigenvalue lambda n. So A hat applied to Vn is equal to lambda n times Vn. Of course, there are many caveats here, so you have to have a complete basis and all that kind of stuff. But usually when we're working with a 2-pi periodic functions, it's not a problem. It's essentially, we kind of sweep this under the rug because we never encountered any problems with that. Okay, so, and also in addition, let me also order all of these eigenvalues so that they are ordered in magnitude from largest to smallest. So then you can build out of this function f naught, you can build the function f1 by simply applying this operator A hat. Note that you don't need to form the matrix of the operator A hat. You just need to be able to apply operator A to a 2-pi periodic function f naught. Right? So if you apply A hat to f naught, you can interchange the summation and application of the operator, and you will get as a result Cn times AVn. A times Vn is simply lambda n times Vn. So you get an expansion similar to this one. Note that lambda naught is the largest eigenvalue in magnitude, lambda 1 is smaller, lambda 2 is smaller than lambda 1, and so forth. And if you factor out the coefficient lambda naught, you would get a C naught V naught plus a sum in which the coefficient lambda n over lambda naught appears. So you'll get lambda naught times C naught V naught plus some remainder after one application. And then if you continue on to iteratively apply this matrix A, this operator A to the functions f. So for example, if you build f sub p of x from f sub p minus 1, you will get something that looks like lambda naught to the power p times the eigenfunction associated to lambda naught plus some remainder Rp of x. And this remainder will have the following form. It's a ratio of lambda n to lambda naught And remember that lambda n is less than lambda naught in magnitude. So this coefficient, lambda n to lambda naught in magnitude is less than 1. When you raise it to large power p, it vanishes, right? The larger p you take, the smaller this coefficient becomes. So essentially this Rp becomes negligible compared to the contribution from C0, V0. If it becomes negligible, then you just throw it out and you say that your Fp approaches to lambda naught raised to the power p times the eigenfunction associated with lambda naught. So you found an eigenpair corresponding to eigenvalue lambda naught and eigenfunction V0 of x. And the cool thing is you never needed to form the matrix of this operator. The caveat, though, is that you only found the largest magnitude eigenvalue, but this can be changed if you introduce the so-called shift-and-invert operator. So remember that if, for example, lambda is an eigenvalue of A, then 1 over lambda is going to be the eigenvalue of A inverse. And if you play this game, but not with the operator A, but rather with operator A inverse, the largest eigenvalue would now become, the largest eigenvalue of A would now be the smallest eigenvalue of A inverse, right? Because if lambda was largest eigenvalue in magnitude, that 1 over lambda would be the smallest. Similarly, if you apply this power method idea to A inverse, you would find the smallest in magnitude eigenvalue of A. But that's also typically not sufficient. Typically, we are interested in the eigenvalue that is closest to a certain point I sigma in the complex plane. So if we are interested in the eigenvalues that are nearest to I sigma, then we can build the shift-and-invert operator, which is A minus I sigma times I, everything inverse. And this operator, its eigenvalue, its largest eigenvalue would be the one that is closest to the point I sigma in the complex plane, right? Because it would result in the smallest denominator, lambda minus I sigma. And in the inverse iteration, 1 over the smallest means the largest magnitude eigenvalue. And this is precisely why we are so interested in the shift-and-invert operator associated with the equation 1. So this operator is exactly the shift-invert version for the operator associated with the stability of Stokes waves. And this operator can be evaluated in n log n steps. Actually, let me step back a bit. So this operator will involve a bunch of operations like multiplying by Stokes wave solution, which can be done in the U space by just multiplying arbitrary function by the solution from the Stokes wave, and also will involve some pseudospectral operator, some pseudospectral operators like applying k-hat, derivatives, Hilbert transforms, that kind of stuff. But also it would involve the inverse of the linearized Babenko equation with some modification. And that has to be done in a similar manner as when we did the solution of the original Stokes wave. Essentially, you would need to solve an equation of the similar form as here. So you would need to also run one either mean-res or conjugate gradient method to solve a linear system that appears in the operator right here. So you would need to do only n log n steps for various pseudospectral operators, but also one solution of a linear system via mean-res or conjugate gradient method, which is also cheap compared to forming the matrix. Okay, so let me also very briefly kind of reiterate. So the method that we talked about right now is in the class of Krylov subspace methods. So Krylov subspaces are spaces spanned by the functions of the form f naught, a f naught, a squared f naught, and so forth. And what we discussed right now is kind of two simple examples, power method and shift-and-invert method, but really there are much more advanced methods that allow you to determine simultaneously many eigenpairs closest to a given point in the complex plane, like shift-and-invert, but not just one eigenvector and eigenvalue, but several at once. The Krylov space-based methods don't require forming the matrix, especially effective for periodic problems where A can be evaluated by f of t's, which is precisely our case. And Bloch/Floquet exponentials are also easily introduced here. So in order to, let me kind of, I'm already out of time, so let me very briefly kind of glance over it. So the eigenvalue problem can be rewritten in a quadratic form as follows. And when we're considering quasi-periodic perturbations, delta y has a form of Floquet exponential times some 2 pi periodic function of u. And you can easily apply each and every operator appearing in this quadratic eigenvalue problem to such an eigenfunction. So, for example, for Hilbert transform, this works as follows. So you plug in for delta y, you plug in e to the power I mu u times p. You write your p in terms of Fourier series for 2 pi periodic function. You throw this exponential under the sum and apply Hilbert transform into each and every exponential that occurs in this sum. So Hilbert transform just gives you the I times the sine of k plus mu. That's that. And that's what you define to be your kind of modified Hilbert transform with the Floquet parameter mu. So that's what you get for this h sub mu times p. And notice also that this e to the power I mu times u, since it does not depend on k, you can factor it back out of the sum. So that's what I did here. And similar game you can play with all the other operators of the quadratic eigenvalue problem. You can do this for omega to 1. You can do this with k hat, with omega to 1 dagger, and also for the linearized Babenko equation. You can also factor this e to the power I mu times u times some modified operator modified with this mu. And the nice thing is that all these self-adjointness properties also carry over for the modified operators as well. So for every value of mu, you still have to solve a problem that's equivalent to the original problem for the co-periodic eigenfunctions. And since I'm already out of time, let me stop here and let me know if you guys have any questions.
Thank you, Sergey. I guess we'll hear a follow-up to this talk next week. Are there any questions about the material that Sergey talked about this week?
Oh, I forgot. Yeah, I forgot to mention. Yeah, the details of the new findings with this numerical method will be presented next week. It's good you pointed it out.
Quick question. Will you talk a little bit about the